Chapter 6 is a continuation of Chapter 5. So it's going to use F net equals ma, Newton's second law of motion, and free body diagrams still. But to the stuff that we learned in Chapter 5, we're going to add friction, air resistance, also known as drag, and circular motion. So we're going to start with friction online, and there's two types of friction that we're going to talk about, and the first of which is static friction or stationary friction. I believe it's a Greek root word, static, and static means not moving. So if you have static electricity is electric charge that isn't moving. It's like stationary electric charge, as opposed to regular electricity, which is moving through wires. Static electricity is charge that's like stuck to a rubber balloon or something like that. So static friction is friction that keeps things from moving. The two main things you have to know about static friction is that the direction of static friction is always parallel to the two surfaces that are in contact and not moving past each other. They're not sliding past each other, usually because static friction is stopping them from moving past each other. And static friction force is parallel to the surfaces in contact. And the other interesting thing about static friction is that it just responds to other forces that act on an object. Let's say you have a heavy weight resting on a table, and you push with a small amount of force left on the heavy weight, and what happens, let's say you push with exactly 3 newtons of force left on the heavy weight, but the weight doesn't move. And the reason why the weight doesn't move is because static friction is resisting your push. And in fact, if you push 3 newtons to the right on the weight, static friction will resist you with exactly 3 newtons to the left. And that's what static friction does. It resists any push that's parallel to the surface in any direction. It'll exactly cancel out any external force. If something has got static friction, it's resting on a table, and you push it sideways, static friction will act to cancel out your sideways push. The only equation we have for static friction is this one, Fs max equals mu s times normal force, where capital N stands for the normal force. Mu s is something called the static friction coefficient, and that's something that engineers have to measure. They actually have to measure what is the maximum static friction force for any two given surfaces, and the normal force applied to those two surfaces, and they measure with some kind of force meter the maximum possible static friction force. So this equation only tells us the maximum possible static friction force, and that's because static friction can usually be any number less than this, because if you only push 3 newtons to the left on a block, static friction will push exactly 3 newtons to the right of the block and exactly cancel out your force. So this is the maximum, this equation says the maximum value that static friction could push. And so what happens if you push with that force? The thing will probably start to slide if you push with just a tiny bit more force. It's the interface between being stuck by friction and sliding. This static friction coefficient called mu s, it's Greek letter mu. It's pronounced like what a kitty would say. Kitties say mu. But it's a Greek letter, and mu sub s stands for static friction coefficient. And it's something that has to be measured for any two given surfaces in contact. Normal force is the force actually pressing the surfaces together. Now usually normal force is the weight of an object set on a table, but physics is clever in that there's some occasions where the weight, if you set an object on a table, the normal force won't be equal to the object's weight. So, for instance, here's an object where of a block sitting on a table, and if the table's on Earth, so it has the force of gravity, W equals mg, pulling down on the table, but the table's supporting that object, so the normal force from the table exactly cancels out W equals mg. So a case where the normal force wouldn't be equal to W equals mg is, let's say, the table is accelerating upwards. So this block is on a table in an elevator that's accelerating upwards, and in that case, normal force is greater than the force of gravity, because remember, not only does the table have to support the block, it also has to provide an additional force to accelerate the block upwards. So that's why it's a better equation that way, because it takes into account of more circumstances. Another circumstance is if somebody is pulling with a string on the block, and except they're not pulling horizontally, they're pulling up at an angle. Notice that if they pull with a string with the block up at an angle, the string actually has a vertical component on the block, and it lifts it up a little bit. The string lifts up the block a little bit off the table, and now the table doesn't have to support the block as much as it would if the string weren't there. So the normal force is actually less in this circumstance if no one was pulling with a string up at an angle. And so, in fact, the maximum static friction force would be a smaller number than if the block was just left alone on the table and there was no string on it. If somebody was pulling it upward at some non-horizontal direction, it would lift up a little bit, and the normal force would be less, and also the friction force would be less. So this normal force in this equation really does capture exactly how much these two objects, namely the block and the table, are being pressed together. And that amount of force is what will determine the maximum possible static friction force. Another case where the normal force isn't equal to the weight of the object is if the object happens to be resting on a ramp or an inclined plane. Remember, the normal force is always perpendicular to the surface, so it's always going to be perpendicular to the surface. So if the ramp or the plane is at an angle from the horizontal, the normal force will be at an angle from the vertical. And this comes into play because the normal force is now no longer pushing opposite the direction of gravity. In this chapter, we're going to pick our x and y axes according to the direction of the acceleration. So if you have an inclined plane, it's likely that the object is going to be sliding up and down the plane. So the x-axis should be parallel to the direction of the acceleration. One axis should always be pointing in the direction of the acceleration of the object, as a general rule of thumb for Chapter 6. So if we do this, and notice what will happen a lot is that oftentimes the x and y axes are going to be slanted. They're not going to be perpendicular to the page. And just because you have to look at every single problem and decide, oh, what's the likely acceleration going to be, and that's the direction that one axis has to point. So we can see, so that's what we're going to do if you have an inclined plane. Nearly always the acceleration of an object on an inclined plane is eventually going to be up and down the plane. So one of the two axes has to point up and down the plane. Now the other thing that will come in very handy for this problem is almost always they'll tell you the angle of incline, and almost always you're going to have to find the y component of the force of gravity and the x component of the force of gravity. And notice you could do a geometric proof and show that if you have an inclined plane and you tilt your x-axis and you tilt your y-axis, and then you went and drew this y component of the force of gravity and this x component of the force of gravity, you could geometrically prove that this angle theta and this angle theta are the same angle. Those are congruent angles. And that means that this adjacent side, this adjacent vector component, is mg cosine theta, and this opposite side is mg sine theta, and that's just using vector components. If we know that angle theta, the opposite side is mg sine theta, the adjacent side is mg cosine theta. Oh, notice incidentally, always in chapter 4, usually the y-axis component always went with sine theta, and the x-axis component almost always went with cosine theta in chapter 4. Chapter 6, that's not always going to be true. In chapter 6, for every vector component resolution problem, you have to look where theta is, and that's going to determine whether it's going to be mg sine theta or mg cosine theta. It's totally legitimate to have mg cosine theta along a y-axis, mg sine theta along the x-axis, even though it almost never was that way in chapter 4. That's totally fine in chapter 6, and it just depends on where this angle theta you know. Now in chapter 6, if you have a plane, they'll usually tell you this angle, and they'll call it the inclination angle, or the angle of inclination. And how you know, and this is really how we do it in physics, is how do you decide what of these, it could be this angle or it could be this angle, that's this angle. And what you should do is you should draw out a little picture and show the inclination angle here, and then look at your triangle and guess between this angle and between this angle which looks closer. So that's how you know which. You look at the picture and you guess, and then you draw in angle theta. And if you don't draw your little sketch with this angle equal 45 degrees, you'll always get it right, or 99% of the time you'll get it right. However, notice that if you draw this angle at 45 degrees in your little sketch, these two angles will look exactly the same. So I encourage you never to draw an inclination angle close to 45 degrees, because then it makes the trick of guessing which is the right angle for your vector components much, much harder. In chapter 6, almost always when we find the normal force, we're going to use the y-axis second law equations. So if I wanted to find the normal force in this situation, I would write F net y equals MAY, and I know that the object isn't going to be accelerating on the y-axis. If this thing is eventually going to slide up and down the plane, it's not going to accelerate in this direction. It's only going to accelerate in this direction, and that in fact is why you're supposed to choose one axis or the other along the direction of acceleration, because then you're guaranteed that the other axis will have zero acceleration. So if I look at all my y forces, notice I'll have plus normal force minus mg cosine theta, because I'm only looking at the y forces, or the y components. So I'm going to have n minus mg cosine theta equals 0, because the y acceleration is 0. And I can see that for a block on an inclined plane or a block on the ramp, the normal force is actually less than the weight of the object. Notice cosine theta is always less than 1, or 1 if angle theta is 0 degrees and cosine theta is 1. But notice, if angle theta was 0 degrees, it wouldn't be an inclined plane, it would be a horizontal plane, and I just get the previous case we've talked about. So notice it's interesting that on an inclined plane, normal force is less than the weight of an object, and it has to be less than the weight of the object, and that's because the normal force doesn't act exactly opposite the direction of gravity. It's actually opposite only this component of the direction of gravity. This has some implications in general. Notice you'll always get less friction, and if you're driving a car, less traction if you're climbing a hill. Right? So there could be hills so steep where your tires just couldn't grip the road. Well, actually, they don't make hills that steep in roads, but off-road competitions, hill climbing is an off-road competition, and so you drive your car up a very steep hill. Depending on the static friction coefficient between your tires and the hill, the normal force might be so small that you just don't get enough traction and your car can't go up that hill. So now in this particular problem, we have an expression for the normal force. It's mg cosine theta. And so if I knew the static friction coefficient of this object on this hill, I could now calculate. I could find an expression. If somebody told me what this number is, and I knew the mass of my object and the angle of the incline, I could now calculate the maximum static friction force that this object could possibly experience. Now, since my only force that's parallel to the two surfaces is this mg sine theta force, that's the only force that's parallel to the surface, is this little component here, mg sine theta. Normal force will act in such a way as to exactly cancel this out. So the static friction must be pointing uphill if this thing is in fact stationary. And what will happen is the static friction will point uphill exactly the same amount as mg sine theta in order to keep this from sliding. Now the reason why we need to calculate what Fs max is if we know the actual number for Fs max, because we know the normal force and we know the static friction. We know a number there. We can compare that number to the value of mg sine theta, right? If mg sine theta is smaller than the maximum possible static friction force, then we know the block is in fact stuck. It's not sliding. And in fact, static friction force will adjust itself to be exactly the value of this mg sine theta force. That's what it does. It exactly cancels out all other forces. So if mg sine theta is less than this number, then we know this block is stuck. It's not sliding. And in fact, if they could ask you, well, what is the static friction force? And the answer is not this equation. The answer is some number less than this equation, and in fact, the static friction force is exactly mg sine theta. Notice it's not going to be this equation. Static friction force will automatically reduce to exactly cancel. It's just barely going to be strong enough to cancel mg sine theta, and it won't be this equation, right? And the reason why we have to know this number is, what if we calculate that mg sine theta is larger than the number we get here? What that means is static friction force is not strong enough to keep this thing from sliding. And what happens is, if we get mg sine theta, this component larger than the maximum possible static friction force happens to be, what will then occur is this block will start sliding downhill. That's why we need to know this equation. That's really the only reason why we have to know this equation, is to detect if an object will slip in a given circumstance or it won't slip in a given circumstance. So in fact, the only time you can actually plug in this actual equation into Newton's second law is if somebody has told you in the problem the object is just about to slip. Right? If the object isn't slipping, what the static friction force will be is whatever the other forces parallel to the surfaces are, static friction force will exactly cancel out those. But if they tell you in the problem the object is just about to slip, or what is the maximum force you can push on the object and have it not slip, that's the only time we can actually use this expression and plug in static friction force in an F net x equation, for instance. The last thing I want to tell you about static friction is that the maximum static friction, Fs max, is in general always greater than sliding friction. So the maximum static friction is experimentally shown to be, for any two surfaces, the maximum static friction is always greater than the sliding friction for those same two surfaces. Now, this is important for cars and for braking in your car, or for race car driving for that matter. And the interesting thing is, when your car tire is functioning properly, the tire is spinning at exactly the right rate, so the bottom of the tire is moving backwards at exactly the same speed the car is moving forward. Now, if you think about it, that's how tires should work. That's how they have to work, provided you're not peeling out. So the bottom of the tire, because the tire's spinning, the bottom of the tire is moving backwards with the exact same speed as the car moves forward. And what this means is that the relative velocity between the bottom of the tire and the road is 0. So when a car is functioning properly, the force of friction between the tire and the road is static friction, and it's not sliding friction. And you might, if you think about it, you know that's true, because sliding friction, what would be going on there is the car's in the process of wiping out, or something drastically wrong has just happened. If the tires are sliding on the road, something wrong is happening. That's not the proper way you should use your car. And this is why actually all modern cars have anti-lock brakes, and the purpose of anti-lock brakes is to, when you do an emergency stop, the anti-lock brakes prevent the tires from sliding on the road, and that's because static friction has experimentally been proven. Actually, let me be specific. The maximum static friction is always greater than the sliding friction force. So you stop in a shorter distance if you have anti-lock brakes. Sadly, my old 1986 Honda Civic doesn't have anti-lock brakes, and so if I do an emergency stop, all four wheels lock up, and in fact I lose the ability to steer, because static friction is also responsible for a large part of the steering in your car. So not only does it not stop as well as a modern car, I love that car, but also when the car locks up, all the wheels are sliding, I also can't change the direction of the car. If I turn the wheels, the car will start spinning, but it'll still be heading in the same direction that I was going before I locked up the wheels. The other thing I want to tell you about static friction force is that Formula One cars have these upside down wings on them. They have a spoiler on the back, and they have a spoiler on the front, and they're actually a very cleverly engineered piece of aerodynamics. And the upside down wings on the Formula One car is they actually fly through the air and they act as wings, and they generate lift, but they generate lift pointing downwards into the ground. And the sole purpose for putting upside down wings on a car generating lift pointing down into the ground is so the car gets pushed down into the ground harder than it would just if it were parked on the asphalt, to increase the normal force from the road, because Formula One racers know that the normal force increases the static friction maximum, and static friction is what gives you traction in a race, right? So that's why Formula One cars, a lot of race cars, have those spoilers, and what they do is they actually generate lift, but pointing down into the ground. So it's not lift, it should be called drop, because it's not lifting anything, it's pushing the thing into the ground. And at race speeds, I think the amount of lift generated, the upside by the Formula One car, is greater than the weight of the Formula One car. Isn't that interesting? That's how much Formula One car drivers value static friction. They want the maximum possible normal force on their car, and at race speeds, the spoilers are generating a force that's greater than the weight of the car. An interesting thing is, so theoretically, you could, in theory, drive a Formula One car at race speeds on the ceiling. Wouldn't that be cool?